Hello guys, welcome to Physics Grad. In this video we are going to continue where we left off in our previous lecture. So this is about constraints and this is the second video about constraints. So let's begin. In the previous video we had seen what are the different difficulties that arise due to constraints, and they are the following. The first is that all the position vectors are now no longer independent. And the second difficulty is that not all the forces are known a priori. Now the details regarding this are already explained in the previous video, so I'm not going to repeat that. And we also saw that for the case of holonomic constraints, the first difficulty can be overcome using generalized coordinates, and that is where we had stopped in the previous video. So now let's consider the case of non-holonomic constraints and let's see what happens. Okay, so as we already know, by definition, constraint equation cannot be used to eliminate the dependent coordinates. So in this case, constraint equations cannot be used to eliminate the dependent coordinates. So this is by definition, because for non-holonomic constraints we cannot express it in an equation which relates the position vectors and say the time. All right, so therefore as we cannot eliminate the dependent variables as we had done for the holonomic case by making use of the constraint equations, because here there is no direct constraint equations which relates the various coordinates. Okay, so to better understand this, let's consider an example. Okay, so first let's consider a general example and then we will see a particular case and see what happens. So if you consider an object which is rolling on a surface without slipping, okay, so object rolling on a surface without slipping. So let's consider this case. Okay, now to represent this, we usually use two sets of coordinates. Okay, so usually two sets of coordinates are used. Okay, so what are these? It will become more clear when we consider a specific case later on this video. So these two sets are the following. First of all, we need some angular coordinates which specify the orientation of the body. So they specify orientation. Okay, and the other thing what we need is obviously the position coordinates of the point of contact. Okay, so we need a set of coordinates which describe the position of point of contact, which describe position of point of contact. Okay, now if you think carefully, you will realize that these two sets are somehow connected by the constraint of rolling. So here rolling is the constraint which connects these two sets of coordinates, and therefore obviously they are not independent. How can I say they are not independent? Because a change in position of the point of contact will force the change in orientation. So they are not independent. It is not that whenever, so the change in orientation happens independently of the change in the position of the point of contact. As soon as the position of the point of contact changes, it implies the object has rolled, which in turn implies that the angle coordinates in turn have changed. So therefore they are somehow connected by the constraint of rolling and are not independent. Okay, so change in position of point of contact will imply change in the angular coordinates. But unfortunately, these sets of coordinates are not related by an equation which is of the form that we encounter for the holonomic case. Okay, so you will understand this better when I consider a particular case soon, okay, in this video. So what I'm trying to say is that yet it's not possible. So even though they are not independent, okay, so previously in the holonomic case, since they were not independent, we could eliminate some of the coordinates. But in this case, even though they are not independent, it is not possible to directly eliminate all the coordinates, or it is not possible to reduce the number of coordinates by just knowing that they are not independent. Okay, so it's not possible to reduce the number of coordinates even though not all are independent. Okay, this is because the connection that we talked about cannot be expressed using an equation of the form given by some function of the coordinates and the angles and possibly time equal to 0. Because if we were able to denote that connection using such an equation, then the constraint would be holonomic. Okay, so all that we know is that because of rolling, all we know is the fact that point of contact is stationary. This is the only information which the rolling constraint is giving us. Okay, so by stationary, it implies that it's a condition on the velocity. So condition on the velocities, because the velocity must be 0. So there is a condition on the velocity, okay? And since velocity is defined as derivative of the position with respect to time, this becomes a differential condition. Okay. So what do we mean by differential condition? We will see when we take up a particular example. Okay. And this differential condition, if we want to convert this into this form, we need to integrate it. Okay. But the integrated form can be given only after the problem is solved. Okay. So, but the integrated form can only be given after the problem is solved. So what do we mean by this? So let's take up a particular example and try to understand this. Okay. So let's consider. So first let me draw the axis Z, X and Y. Okay. So let's consider a disk that is rolling on the XY plane. So disk rolling on XY plane. Okay. So it rolls like this, let's say. So this disk may roll and follow some particular path like this. Okay. Now to denote this, as we had already seen before, we need two sets of coordinates. One of them is the angular coordinates to describe the orientation, and then the position coordinates to describe the point of contact. Okay. So we are going to denote the angle made with respect to the x-axis as theta. Okay. So actually, so let me draw it more clearly. So this is our x-axis, this is the path. So the angle made will be theta. The angle made with the x-axis will be theta. Let's denote it as theta. And if this is the center of the disk and with some reference like this, then I am going to call this angle, okay, as phi, and the position of the center of the disk I am going to denote as x comma y comma z, which implies the position of the point of contact is just x comma y. Okay. So we have theta, phi and x and y, which denote, so this denotes the orientation and this denotes the position of point of contact. Okay. Then we can easily see that the velocity of the center of the disk, okay, is going to be equal to the radius of the disk. So if a is the radius of the disk, so it's going to be a times phi dot, that is the angular velocity. So the linear velocity of the center of the disk is related to the angular velocity through its radius in this form. Okay. Then from this we can get if you see So Vx, that is dx by dt, is going to be simply V sine theta. So if this is V, and if I draw a perpendicular to the x-axis here like this, then this will be 90 minus theta, right? Then the x component of the velocity will be nothing but, so if this is theta, this is 90 minus theta. So what will be V sine theta? So this, the tangent to this curve will be the direction of V, and this theta, the line which joins this the point of contact and the x-axis, this angle is actually this line. So this line is parallel to axis of the disk. So if you just consider the two-dimensional picture here, yx, then if this is the curve and this is the point of contact, this is the tangential direction of the velocity, and the axis of the disk is going to be perpendicular to the tangent. So this is 90 and this angle is defined as theta. So now if I draw a perpendicular to the x-axis from the point of contact, then this angle is going to be 90 minus theta and this angle is going to be theta. So the x component of the velocity Vx is just going to be, so this in turn will be 90 minus theta, so it is going to be V cos theta, and that V sin theta, or V cos 90 minus theta, which is V sin theta, which is what we have here. And by the same argument we will get Vy is equal to dy by dt is equal to minus V cos theta. Okay, so we have x dot is equal to V sin theta and y dot is equal to minus V cos theta. Okay, but we know that it is equal to a phi dot, so this will become x dot equal to a sin theta phi dot and y dot equal to minus a cos theta phi dot. So this becomes dx equal to a sin theta d phi and dy equal to minus a cos theta d phi. And this is what we mean by this. So here I had noted that the condition is going to be a differential condition, and that is what we have got here. So this is a differential condition. Okay, now if we wanted this, so to get this in the form of f of x, y, theta, phi equal to 0, what do we need to do? We need to integrate. Okay, but from where to where and along what? So how do we integrate? To integrate this, we need to know the path of the curve, right? Because we need to integrate it along the path. So to integrate, we need to know the path. right? Because only then we will get this thing, only if we integrate. So when I integrate, we need to know from where to where and also along which path. But knowing the path is basically we need to solve the problem. Okay, and that is what I meant by this statement here. So the integrated form can only be given after the problem is solved, and that is what we also got in our example. Okay, so therefore unless the problem is solved, we cannot express it in this form, and therefore this is a non-holonomic constraint. Okay, now as we had already seen, this is not the only form in which we can express non-holonomic constraints. We can also have equations involving, I don't know, higher derivatives or inequalities, as we have already seen. Okay, so we can also have non-holonomic constraints which involve higher degree or higher order differential equations. Okay, so higher order differential conditions in this case it was of the first order, or we can also have inequalities. So what I mean, where I'm going here, is that how we represent the non-holonomic constraint is basically dependent on the problem, and there is no general recipe to make the problem simpler. Okay, so therefore in the case of non-holonomic constraint, there is no general way of simplifying the problems involving non-holonomic constraints. Okay, because depending on the problem, they will be described using different types of conditions or inequalities, and in almost every case, to get from these kind of conditions to the equation of this form, there is no other way other than solving the problem. Okay, so that is how we deal with the first difficulty in the case of holonomic and non-holonomic constraints. But what about the second difficulty? What about the second difficulty, that is, not all forces are known a priori? How do we overcome that? Okay, so how to overcome this? Now, if we had to use Newton's law, okay, if we have to use Newton's law, okay, then this is going to involve all the forces. Okay, so in order to use the Newton's law, we need to involve all the forces which are not known. That is the difficulty that we have here. Okay, so one way of solving this is to define or formulate the problem which do not involve these constraint forces. Okay, and one way of doing this is to use the principle of least action, because principle of least action does not ask you any information regarding the forces that are involved. All that we need to know is define the Lagrangian for the system, and from this we solve the Euler-Lagrange equations, from which we get the equations of motion, from which we get the trajectory which we are interested in. Okay, so to solve the second difficulty of not knowing all the forces which are involved in the constraints, we make use of the principle of least action and the Euler-Lagrange equations to finally end up with the trajectory of the particles or the system. Now, in the future videos, we are going to explore some problems which will make this point more clear. So that's it for this video. Thank you for watching. See you next time.